Hi, in this video we will learn how to differentiate functions which are implicitly defined. In general, when we say y is a function of x, this dependence can be given through two completely different approaches. One is, it's called y is defined explicitly. It means what? It means that we have a function, an expression in x, like f of x, that y is equal to that. But there is another alternative for this, that y is implicitly defined. It means that y is not given explicitly as an expression of x. There is an equation, so an equation in both x and y defines the dependence. So the way y depends on x is given through an equation, and we have to go through that one. For example, that equation can simply be, well, any equation in xy basically will be an option for us. But for example, in this case, I can have x squared y plus x equals to 1. Or we can have x squared plus y squared equals to 5. Well, what we have here is both of them are equations in x and y, and through this y can be given as a function, or depends on x. However, sometimes we can turn these guys into explicitly defined function. For example, look at this guy. I can solve this for y. Y is 1 minus x over x squared. But for this other one, there is no way we can do this, because y is going to be plus minus 5 minus x squared. So basically, this equation does not give us an explicitly defined function. There are ways to make sense of this, how this is a function of x, but definitely not explicitly. Okay. Now, the goal is what? The goal is differentiate implicitly defined functions without taking them into explicitly defined form, which won't be easy at all. For example, we will go through an example and then show the steps. The goal, let's just start with the one that we have, x squared y plus x is equal to 1. The goal is what? The goal is to find derivative of y with respect to x. So we are looking for dy dx. That's the goal, yes. I'm saying here, what I suggest here is that differentiate both sides with respect to x. So that is differentiate both sides with respect to x. Well, means what? Means that take this guy, d dx, to the left of the equation, to the right side of the equation. And then we'll apply the differentiation rule. So this will be some rule, and the right hand side derivative of constant function is 0. Then product rule, and here you see that derivative of x squared is 2xy plus x squared. Derivative of y with respect to x, which we can just write dy dx. And derivative of x with respect to y is 1. So here's the key point. When you start with an equation in x and y and you differentiate with respect to x, at the end you're going to get an equation for dy dx. So an equation, this is an equation for dy dx, the first derivative of y with respect to x. Now solve that equation for dy dx. That's the goal we have. So solve it. Here, what I have, okay, let me go back to the blue one. What we have is x squared dy dx. Isolate this guy, yes, minus 2xy, and then divided dy dx minus 1 minus 2xy over x squared. And we found dy dx in terms of, we found dy dx. That's the derivative, yes? So we just differentiated both sides of the equation and solved it for dy dx. Well, you may say that, okay, what kind of derivative is this thing? Remark 1 is that, well, when you start with implicitly defined function, the derivative will have not only x, but also y. So the derivative of an implicitly defined function will be in terms of x and y. Well, the function itself wasn't given explicitly in terms of x, so how you're expecting the derivative will be explicitly in terms of x? If we'll have both x and y like you see here, then another thing is that, well, this function that we started with, we can differentiate that one. So the function we had here was what? Let me just write it down. Was y x squared y plus x equals to 1. We can differentiate this, find y through this 1 minus x and x squared. And then we can differentiate this guy. This is actually, we can simplify a little bit more. This is actually is 1 over x squared minus 1 over x. Well, if it is explicit, if it can be written explicitly in terms of x, then differentiating is not difficult. This will give us actually negative 2 over x 3 plus 1 over x squared. And well, this is x cubed minus 2 plus x. You may compare these two things. Once doing implicit differentiation, we got dy dx is negative 1 minus 2xy over x squared. And once we did by explicit expression for y, we got negative 2 plus x over x squared. Which one of these guys are going to be the correct one? Well, actually, what happens here is that these are same things. There is a y here. If you plug in y to be equal to what? 1 minus x over x squared, you will see that this expression will turn into this other one. The presence of y in the first formula makes it a little bit different. So in the form, when you look at them, they might be different, but at the end you may get exactly same value. Try this one. Try to plug in y as 1 minus x over x squared. So that was the remark 2 that I wanted to mention. Well, now that we did one example and we saw what is going on in this case, let's write the steps of the implicit differentiation. So this is called implicit differentiation. So an equation in x and y is given, and the question asks us to find dy dx. Okay, what we do? Step 1: differentiate both sides of the equation with respect to x. So start differentiating with respect to x. Step 2 is that, well, when you get to terms which have y or powers of y or some functions of y, apply the chain rule. So apply the chain rule to the terms with y. For example, if you have y while you're differentiating, you write what? Dy dx. That's the obvious one. But if you have, for example, y to the power n d dx, you write n y prime y to the power n minus 1, and so on. So the chain rule you have to apply. In general, what I meant was that d dx of, if you find an expression in y, you have to do y prime g prime of y. Okay, so this way then you have everything written, and there will be an equation in dy dx. Then step 3, solve the equation for dy dx or y prime. Solve the equation for that. It means what? It means that take all the terms which have dy dx as multiple one side, take everything else to the other side, factor dy dx, divide the multiple, the coefficient of dy dx to the right hand side. In other words, isolate dy dx, and this will be always possible. Okay, so this way we find dy dx, an expression in x and y. Okay, let's do one example, maybe two examples. Example: find dy dx if xy plus y squared is equal to x plus 1. Okay, so let's start with the steps. Step 1, differentiate both sides with respect to x. So dx xy plus y squared equals to ddx of x plus 1. Apply the rules, yes, differentiation rules. So this will be x y plus x d y dx. This is product rule. And then dy squared with respect to x, and then this is ddx of x plus ddx of 1. Now, derivative of x with respect to x is 1 times y plus x. Derivative of y with respect to x, well, just write dy dx for this, plus derivative of y squared with respect to x. This is 2 dy dx times y to the power 2 minus 1. That's the chain rule. And derivative of x with respect to x is 1. Derivative of 1 with respect to x is 0. So this, let me just write it in simpler way. So 2 dy dx, y is equal to 1. Now you look at this equation, you see that this is an equation for dy dx. By the way, I applied step 2 here whenever I saw, whenever it came to the derivatives of y or an expression in y, we use the chain rule. And here now we have step 3. We have to solve that equation for dy, isolate dy dx. So this means that dy dx, these two terms have dy dx, factor this out, take the other terms to the right hand side. Now from this, dy dx is equal to 1 minus y over x plus 2y. And that's the derivative of the function implicitly defined by that equation. Okay, so definitely we will do more examples, but here comes the fact that, okay, if this equation gives us a curve, which definitely gives us a curve, I can use this derivative and find the slope of tangent line and find an equation for the tangent line. So let me write this as a remark. So the equation which defines y implicitly as a function of x also defines a curve, the curve on the plane. The derivative dy dx at any point of this curve gives us the slope of the tangent line to that curve at that point. For example, find an equation for the tangent line to to the graph, to the curve, the one we just worked with, xy plus y squared equals to x plus 1 at 1, at point 1 and negative 2. Okay, you see that we need a point. The point is here. This is x, this is y, and we also need the slope. Slope here is dy dx. We have to plug in x equal to 1 and y equal to negative 2. So that is the slope we are looking for, m. Here, we already found dy dx, so it is 1 minus y over x plus 2y. At what point? When x is 1 and y is negative 2. So let's plug in these values. 1 minus negative 2, 1 plus 2 times negative 2. That gives us the slope 3 over negative 3, which is negative 1. So we have the slope negative 1, x1, and point this. Then we can write y minus y1 equals to m, x minus x1, which gives us y minus negative 2 equals to negative 1 times x minus 1. And this is y plus 2 equals to minus x plus 1. And simplify one more. This is minus x plus 1 minus 2 minus 1. And that is an equation for the tangent line to the curve defined by this equation. Well, this brings us to the end of this video, in which we learned how to differentiate, find dy dx of a function implicitly given. And we saw that there are three main steps we have to apply, and then we find it. It can be used as the slope of the tangent line to the curve defined by the equation.